Lesson 4.6, the fundamental theorem of algebra. The fundamental theorem of algebra talks about how many solutions there are for a polynomial equations. It says a polynomial function of degrees greater than 0 has at least one 0. Wow! So if you have a polynomial, there's at least one 0. Yay! Those zeros, however, might be imaginary. There is the same number of zeros as is the degree, but you might have the same 0 more than once. For example, here the degree is 2, so we'd expect 2 zeros. However, if we solve by factoring, we'd factor this and you get x plus 3 times x plus 3. Take each of those equal to 0. Get x is negative 3 and x is negative 3. Look at that, you have the same answer twice. You have two answers, but they happen to be the same number. We count them twice as far as the fundamental theorem of algebra is concerned. So how many solutions does this equation have? And then find them all. Well, the degree, highest degree is 4. So there should be 4 solutions. Now we're supposed to find them all. Looking at this, I would like to try factoring. I don't want to do the p's and q's unless I absolutely have to. So I'll look at this, and I think I probably can do factoring by grouping. So out of the first group, I can factor out an x cubed, leaving x minus 5. Second group, I can factor out a 1. I know, that's exciting, but anyway. All right, now the x minus 5 is in both terms, so I can factor out the x minus 5, leaving x cubed plus 1. But the x cubed plus 1, that's the same as x cubed plus 1 cubed. So that is a sum of cubes. So that is x plus 1. If you don't remember the pattern, you can go back and look it up. X squared plus x plus 1. All right, then I take each of those equal to 0. So each factor equal to 0, and solve each of those. So I get x is 5, I get x is negative 1. We've already factored as far as we can, so we're going to have to use the quadratic formula. It'll be negative b plus and minus the square root of b squared minus 4ac over 2a. So that'll be the square root of negative 3. The square root of a negative is I, so it'll be square root of 3 over 2i. So our answers are negative 1, 5, negative 1 plus the square root of 3 over 2i, and negative 1/2 minus the square root of 3 over 2i. And look at that, we have 4 solutions. Let's try another one. Find all the zeros of this function. This one doesn't factor, so that means we're going to have to do the p's and q's. Remember, p's are factors of the constant term, so that'd be the negative 10. So that'd be plus, and that'd be 1 times 10, or 2 times 5, and that's it. Q's are factors of the leading coefficient. In this case, it's just 1. So the p over q is the 1, the 2, the 5, and the 10. All right, so now we need to decide what to try with our synthetic division. If I do a quick graph on my graphing calculator, I see that it looks something like this, where that appears to be 1. So I'm going to try a 1. 1x cubed minus 7x squared, 16x, and negative 10. Bring down the 1 and multiply, add, multiply, add, multiply, add. Hey, look at that, we got a 0. That was x cubed, so now it is x squared. Since it's squared, maybe we can factor it. Times what makes 10? I want to multiply to get 10 and add to negative 6. So 2 and 5, no, 2 and 5 doesn't work. That makes 7. How about 1 and 10? No. So it looks like we can't factor it. So if we can't factor it, we'll have to use the quadratic formula. Be negative b plus and minus the square root of b squared minus 4ac over 2a. Square looks like it's 36 minus 40, or negative 4. So that would be 6 over 2 plus or minus the square root of 4. Square root of 4 is 2, and then the I. So it appears to be 3 plus or minus I. All right, how many solutions should we have had? That's right, we should have had 3 solutions. How many do we have? Well, we have the 1 right there. We have 3 plus I and 3 minus I from right there. Look at that, 3 solutions. If you noticed in the last problem, in fact the last 2 problems, we ended up with something plus and minus I. It gives us the complex conjugate theorem, which says the complex number a plus bi is a 0, then a minus bi is also a 0. That means that the complex zeros come in pair. It's always something plus and minus something I. Also happens to be true for the irrational zeros, the square roots. And both of that, as far as we're concerned, occur because when we use the quadratic formula, you know, it's the plus and minus. But otherwise, these always come in pairs. The rational zeros, those are the p's and the q's, could be single, but complex, irrational must be in pairs. So now that we know that, let's write a polynomial function that has these zeros, 2 and 4i. Well, we have the 4i, it's imaginary. That means we also have its conjugate, which would be negative 4i. All right, if those are the zeros, then x minus the 0 gives us our factors. So we have that. Now let's multiply them together. Now it's easiest if we multiply the imaginary ones first. So the x minus 2 is just going to hang out. X times x, x times 4i, negative 4i times x, and negative 16i squared. Remember, I squared is negative 1, so that's like it's plus 16. Those cancel out, so it'll be x squared plus 16. Multiply these, I get x times x squared, x times 16, negative 2 times x squared, and negative 2 times 16. Of course, we usually write this in order of descending exponents. So it looks like that. Notice there are no i's in our answer. It's real coefficients. Real coefficients. So now that you know how to do the p's and q's and finding the zeros with those, maybe it'd be nice to shorten the list. Let's say you don't have a graphing calculator handy. You like to shorten the list of things you could try. Well, Descartes came up with this rule of signs a long time ago, and it does give us a shortcut. If f of x is a polynomial function, then the number of positive real zeros is equal to the number of sign changes in f of x, or less by an even number. Like, huh? Yeah, you'll see how this works. But we also need the number of negative real zeros. Hey, notice only the things in bold changed. Everything else says the same. So if we have just f of x, that'll give us the positive number of real zeros. If we have f of negative x, that'll give us the number of negative real zeros. So let's determine the possible number of positive real zeros, negative real zeros, and imaginary zeros for this function. So let's start with the number of positive zeros. So we're going to look at the function and look at the coefficients and see how many times the sign changes. So like there, it goes from positive to a negative, so that's 1. That goes from a negative to a positive, so that's 2. Positive to negative is 3, and negative to positive is 4. So it is 4 positive real zeros. Or it said less by an even number. So if I subtract 2, because maybe 2 of them are imaginary, we'd have 2 positive real zeros. Or maybe we have another pair of imaginary zeros. So what you do is you get your number and you just keep subtracting by 2 until you reach 1 or 0. Why? Because maybe some of the zeros are imaginary, and the imaginary zeros always come in pairs. That's why we're subtracting by 2. To get the negative real zeros, we'll need g of negative x. And we're going to get that by plugging in a negative x for x. So replace x with negative x. When you have negative to an even power, it becomes positive. Negative to an odd power stays negative. So here we'll have negative 3 times negative x cubed, which makes it positive x cubed. Negative x squared is positive x squared, but here I have negative times negative, which makes that positive. And now count the sign changes. Wait, there aren't any. So there are 0 negative zeros. So if you were doing the p's and the q's, we could just eliminate all the negative choices, cut our list in half. That doesn't always happen, but in this case it did. So we could summarize in a table. If we have 4 positive real zeros, no negative real zeros, notice it's x to the 4th. So we always have 4 total zeros. So 4 of them are positive and none are negative. That are 0 left for imaginary. If I add these together, I have to get the 4. If there are only 2 positive zeros and no negative zeros, I would have to have 2 imaginaries to equal the 4 total. If I happen to have no positive zeros and no negative zeros, that means I'd have to have 4 imaginary zeros in order to get my total of 4 zeros.